Welcome. The topic we'll be discussing in this lecture is red black trees. So in the last lecture we have discussed about AVL trees, and before that we have discussed about binary search trees. So how could we define red black trees? What is red black trees? Why should we study this? First let us try to understand that. Red black trees are also binary search trees, and red black trees are self-balancing binary search trees. Okay. Red black trees are self-balancing binary search trees. So in that context, it is similar to an AVL tree. AVL tree is also an self-balancing binary search tree. Okay. So again, why should we discuss red black trees? Already we have discussed AVL trees, which is a self-balancing binary search tree. Then why should we discuss red black trees? The answer for this question is yeah. Even though AVL tree is a self-balancing binary search tree, and all operations in AVL trees can be performed in the order of log n times. But still, there is one drawback with AVL trees. The drawback is it involves a lot of rotations. It involves a lot of rotations, and these rotations are costly operations. And these rotations are costly operations. So, under which condition AVL trees are best suitable in the sense if if the tree is once created, okay. So initially, when you create the tree, there may be any number of nodes, say 100 nodes are there, or even 1000 nodes are there, okay. And when you create the tree, when you create an AVL tree, there may be some rotations, either LL kind of imbalance, or RR, or LR, or RL, whatever it may be. The specific rotations will be carried out, okay. Say once for all, once you create a binary tree, binary search tree, or an AVL tree, say after that the probability of inserting a new node is very less, and only you will be using the AVL tree only maximum you will be using it for searching. In that case, AVL trees are suggestible. Okay, so AVL trees actually it performs better. It performs better when there are less insertion. Okay, when there are less number of insertions or deletions. Okay? During deletions also the tree will get imbalanced. And when there are more and when there are more number of search operations. Okay. So in that context, AVL trees are suggestible. Okay. Because insertions are less, or whatever the insertion you do it once at the beginning. After that, the probability of inserting a new node is very less, and mostly it will be used for searching a particular node and where it is available. And in that case, the search operation can be done in order of log n times. So in such situations, AVL trees are best suitable. Okay, but if there are more insertions, if there are more insertion than the search operation, then actually the performance of the AVL tree will come down. Okay, so in that context, we are discussing red black trees. Okay, so because of that, the red black trees comes into picture. Okay, so red black trees are also self-balancing binary trees. These are also uh, self-balancing binary search trees. Okay, self-balancing BST binary search trees. Okay, but what it does in the sense, in red black trees there are two. We whenever the tree get unbalanced, the rebalance is done in two ways. There are two ways to rebalance the unbalanced tree. Okay, there are two methods of rebalancing the unbalanced tree. The first method is by using something called as recoloring. The first method is by using a technique called recoloring. This is the first method to rebalance. And the second method to rebalance is again by rotations. Okay. These rotations are very similar to that of AVL tree. There is no difference. Okay. But here what happens is the number of rotations will be less. When compared to AVL tree, the number of rotations that will be done on a red black tree for rebalancing, it would be less. Okay, because every time when the tree get unbalanced, we don't go for rotations. First we check whether the tree can be rebalanced just by recoloring. Whether the tree can be rebalanced just by recoloring. If the job can be done, that is, if the tree can be rebalanced just by recoloring, then we won't go for rotations. Then we won't go for rotations. So, so the number of rotations that will be performed on a red black tree will be less when compared to that of an AVL tree. Okay, and this rebalancing is not an recoloring is not an costly operation. Recoloring is not an costly operation. It is just changing the color of a node. So we will maintain a variable in every node which represents the color of the node. So every node can be either in red color or in green or in black color, so that it is red black trees. Okay. So each nodes should be either it should have either red color or it should have black color. Okay. So in the first method of rebalancing, what we do is we just change the color. We change the color of a node from either red to black or black to red, something like that. Okay. And by that we ensure that the tree got balanced. Okay. Let us go into the details on how exactly it happens. All these things we'll discuss in the course of the lecture, but I'm trying to give you a brief understanding of what is happening. Okay. So here color, in the sense, we are not going to literally color the node. We are not going to literally color the node. So what we will do, in the sense, we will introduce one more variable. We will introduce one more variable, and that will represent the color of the node. Okay, this is how normally we define a binary search tree or an AVL tree. Okay, int key struct node L child and or child. Right. Along with that, we will keep one more variable, and that variable is obviously in AVL tree we maintained height. Okay, here I don't think height is required. Okay, let us keep. We'll see what happens, and then one more variable you should maintain, that is called as color of the node. Character, say color. Okay, this color can take two values, either black or red. Okay, okay. So this is the introduction to red black trees, right? So why we are going for red black trees, in the sense, red black trees are also similar to AVL trees in the sense that red black trees are also self-balancing binary search trees. But AVL trees are best suitable when there are less number of insertions and when there are more number of search operations. If there are more insertions and there are less search operations, then AVL trees are not suggestible because the insertion operations are quite costly. So in that context, we are going for another kind of trees, which is called as red black trees. And red black trees are called as self-balancing binary search trees. Here, unbalanced, whenever the tree get unbalanced, for rebalancing, we follow two techniques. Either the rebalancing will be done by recoloring or it will done by rotation. Okay. So whenever rebalance occurs, first we will try to whenever the tree get unbalanced, first we try to rebalance by using recoloring. Only if recoloring does not work, then only we'll go for rotations. Okay. So by doing that, what happens, in the sense, the number of rotations that is done on a red black tree will be less when compared with the AVL trees. Okay. So so in terms of performance, red black trees can will perform better than AVL trees. Okay. This recoloring is not a costly operation. It is a less cost operation. Okay, it is just changing the value of a variable. So with every node, we associate one variable called color, which represents the color of the node. Okay. So with this introduction, let us move to the concept. Right. So in a red black tree, as we have already discussed, every node should be colored either in red color or in uh, black color. So red black trees are also binary search trees. It is a self-balancing binary search tree. Each node is colored as either red or black. Okay. Root and all external nodes are black. Okay, the root node will be always black. So there are certain rules for coloring. So the root node should be always black, and the external node should also be always black. Okay. Actually, here external nodes, in the sense, normally we refer to leaf nodes. Okay. Normally we refer to leaf nodes as external nodes. But in red black trees, actually here external node in the sense we are not talking about the leaf nodes. We are talking about the child of the leaf node. Okay. Yeah, there are no child for leaf node. Okay. There are no child for leaf node. Say for example, if in this particular tree, if D is the leaf node, then D does not have any child, right? So here we will represent as null. Okay, we will represent as null. That is D's left child is also null. D's right child is also null. Similarly, we don't know about B. B may have children, or and C may have another children. Okay, let us assume D does not have any children. D is a leaf node. In that case, in red black trees we won't stop with D. Rather, we mention the null pointer of the D also. Okay, its left is also null and its right is also null. Okay, so this null pointer we will represent in black color. These null pointers we will represent in black color. Okay, so this is what here external nodes means. Okay, so uh, so you should remember that in generally when you talk about any trees, external nodes refer to leaf nodes. Okay, but in red black trees, when you say external nodes, actually it refers to the null pointer, the left and the right null pointer of the leaf nodes. Okay, and that we assume that it is black. Okay, we assume that these are in black color. Okay, so actually here we are discussing the properties of a red black tree. What are the properties or what are the conditions for a red black tree, right? So the first thing is each node should be either red or black in color. Root and all external nodes should be in black. No root to external node path has two consecutive red nodes. Okay. So if you travel from the root node to the root node to the leaf node, okay. When you travel from the root node to the leaf node, in the path there should not be two consecutive red nodes. So what is when the consecutive red nodes? That means a parent and a child should not be colored as red. Okay. Say, okay, I will use a different color because I'm using red here. I'll take black. So the root should be black. Okay. Say, say the next child. Say this child is uh, also black. Okay. Say this right child. Say it is also black. Say the this child. Say it is red. Okay. Say this child is red. Say this child is red. Okay. Fine. So say its right child is also red. Okay. Fine. Something here. Okay. It is X or and this is Y. Okay. Now Y's children or X children cannot be red. Okay. Y the child of Y or child of X cannot be red. Okay. That is what it says. No two consecutive from when you travel from root to external node. Okay. No two adjacent nodes should be red in color. Okay. Here adjacent in the sense child and parent. These two are not adjacent. Y and X are not adjacent because they are siblings. Okay. So here if I keep another node Z, this Z should not be in red color. If the Z is in red color, then it means that you are violating the principle of red black tree. It means you are violating the principle of red black tree. So this Z should be in black color. Okay. Suppose if Z is a red color, then we say that the tree is unbalanced. Okay. If Y is red and Z is also red, then we say that the tree is unbalanced, then you have to rebalance. Okay. For rebalancing, either you have to do recoloring or you have to do rotation. Okay. So this is the third property which says that no two adjacent nodes should be of red color. Okay. Adjacent here in the sense we mean that it is parent and child. Okay. Right. But two adjacent nodes can be of black color. That is fine. That is acceptable. Okay. And the last property is all root to external node paths should have same number of black nodes. Okay. When you travel from the root node to the external nodes to the external node, the number of black nodes you encounter should be same on every path. Okay. Okay. This is the fourth condition or the fourth requirement. When you travel from the root node to the external nodes, the number of black nodes that you visit should be equal in all the paths. Okay? So these are the properties or what you call or principles of a binary search tree. with respect to the color of the nodes. With respect to the color of the nodes. So, so a binary search, it is a binary search tree. Every node should be red or black in color. Root and all external nodes are black, and node to adjacent node should be in red color. Okay. So when you travel from root to the external nodes, the number of black nodes that you will be visiting should be same in all the paths. Okay. So uh, so these are the four properties with respect to the color of the nodes. Similarly, we have another four properties with respect to the color of the edges. So edges are the one which connect one node to another node. Okay. So with respect to color of the edges, also we have some guidelines or principles. Okay, the child pointers, the edges means the pointers, right? So say for example, this is a node, this is another node, so this is edge. So this edge is nothing but a pointer. Okay. The child pointers are colored red or black. These pointers also will be colored. This also will be colored either red or black. Okay. If it is pointing to a red child, it will be colored as red. If it is pointing to a black child, it will be colored as black. Okay. If this is a red child, say I'm mentioning as or, then this pointer will be in red color. Okay. If this is a black child, then this pointer will be in black color. Okay. So that's the point. Okay. And pointer to an external node is black. So external node, as I already said, if C is external node, then it means that, I mean, if C is the leaf node, I mean, that means the node which does not have any child, then C's left and right pointer will refer to null. Okay. So this null actually we are calling as external nodes. Okay. So the pointer to this null node should be black in color. Okay. So in red black trees, external node means we refer to the null nodes. And pointer to the null node should be black in color. Okay. No route to external path has two consecutive red pointers. Okay. So this is same as that of the previous condition. Like how we discussed that node to from root to external node, there should not be two consecutive red nodes. Similarly, there should not be two consecutive red edges. If this is a red edge, then the next edge should not be red. Okay. Okay. Because there cannot be two red nodes consecutively. So obviously, you should not have two red edges also. Okay. So if this is a red edge, and this is also a red edge, then that is not allowed. Okay. And the fourth is every route to external node path has the same number of black pointers. Okay, from root to external node, if you count the number of black pointers, the number of black pointers should be same. Okay. So these are the definition for edges. Okay. Previously we discussed the definition for nodes. Colored definition. These are the colored definition for nodes, and these are the colored definition for edges. Okay. Fine. So for implementing, both the things are not required. Any one is enough to implement the red black trees. Okay. You can go with either node definition or with edge definition. Okay. Or simply you can say that if a edge is pointing to a black node, it will be in black in color. If edge is pointing to a red node, it will be in red in color. Okay. And whatever the definition we discussed for nodes, that is also applicable for edges. Okay. Like edge should be either black or red in color, and no two consecutive edges can be of red in color. And when you count the black edges from the root node to the external nodes, it should be same on all the paths. And an edge to an external node, that is to a null node, should be always in black color. Okay, because null nodes are in black color. Right? Fine. So this is an example of a red black tree. Here, so here you can see that these are the leaf nodes: 1, 5, 8, 20, 25, 35, 60. All these are leaf nodes. 45 has only one child. Okay, but you can see that all the null are represented as black nodes. Okay, so actually these things we call it as external nodes. In the context of red black trees, we call these null nodes as external nodes. Okay, and you can see the pointers for the null nodes. It is in black color. Okay, it is in black color, right? And you can see the pointers of the for all the red nodes. It is in red color. Okay, and and if you count the number of black nodes or black edges from the root to the external node, it will be same on all the path. For example, let us take this path. Number of black nodes, it is 1, 2, 3, 4. Okay, including the external node. So it is 4. Let me take some other path. Let me take this path. Okay, 1, 2, 3, 4. Here also it is 4. To take any path, it will be 4 only. 1, 2, 3, 4. This path is also 4. Okay. If you take this path, 1, 2, 3, 4. So in any path, it will be the number of black nodes you visit will be same. Okay. Similarly, if you want, you can check for edges also. Okay. So if these properties are matching, then it is a red black tree. And also there should not be consecutive red nodes. You can see this is red, its parent is not red, its child is also not red. This is red, its parent is not red, its child is not red. This is red, its parent is not red, its child is not red. This is red, its parent is not red, its child is not red. This is red, its parent is not red, its child is also not red. So if all these four properties are matching, you can compare either with respect to the node definition or with respect to the edge definition. Any one definition you can check. Okay, that is fine. And if all the four properties were matching, then we will say that it is a red black tree. Okay. First property is the node should be colored either red or black. Okay, all nodes are colored as either red or black. Second is the leaf nodes should, I mean the external node should be black. All external nodes are black. Done. Third is the number of, no two adjacent nodes should be in red in color. Okay, so that is check that we have checked. No two adjacent nodes are in red color. There is no two child and parent are in red in color. Okay. And the fourth condition is the number of black nodes that you encounter from root to the external node should be same in all the pods. It is same in all the pods, right? So these are the what do you call? These are the uh, conditions for a red black tree. So there is another property. The height of a red black tree that has n nodes will be somewhere between log n plus 1 to 2 log n plus 1 to the base 2. Okay. So we are not going to discuss any proof for that. Okay, this is just for information. The height of a red black tree, which has n nodes, will be somewhere between this. It will be between log n plus 1 to the base 2 and 2 log n plus 1 to the base 2. Right? There is another property which says that start with a red black tree whose height is height h. Okay, take a red black tree whose height is h. Collapse all red nodes into their parent black nodes. Okay. So when we say it's a red black tree, only if they don't have a consecutive red nodes. That is one of the property, right? So the parent of the red node will be a black node. Okay. So you take a red black tree with height h and go to every red node, visit every red node. Okay. Its parent will be obviously a black node. Collapse this red node onto the black node. Okay. Collapse this red node onto the black node. That is, let us assume that the red node got merged into the black node. Okay. When you do that for all the nodes, when you do that for all the nodes, then the height of the tree will become, well, then the height will become something greater than or equal to h by 2. Okay. That is, previously the height is h. Now the height can reduce up to h by 2. Okay. It can go down maximum up to h by 2. Okay. Right? That is, if the previously if the height is 10, now the height will be it will be greater than or equal to 5. Exactly, it depends on how many red nodes are there. Okay, and after performing all these things, all external nodes will come in the same level. Previously, all external nodes may not be in the same level, but after doing this, all external nodes will come in the same level. Right? That is, take a red black tree with height h, visit all the red nodes, and collapse that red node to its parent black node. When you do that, its height will become somewhere between h by 2. It will just become greater than or equal to h by 2, but it will never become less than h by 2. And all the external nodes will come at the same level. Let us discuss this with an example. Take this particular binary search tree. Okay. Now if you collapse, this is the red node, right? If you collapse this red node to the parent black node, then this will got merged here. Okay. This one will get merged here. Then these two child nodes, I mean these two external nodes will move up by one level, right? Similarly, when you merge this 5 here, this 5 will got merged into 3. Then these two uh, external nodes, okay, or these two external nodes will become one external node, right? These two external nodes should become one external node, right? Because we are discussing about binary trees, right? So they will come in this level, okay? So this will become one external node, this will become another external node, okay? Right? Here there is no, what do you call, red. So here is a red, here is a red. When you merge this red here, when you merge this red here, what will happen? These two external nodes will come here. Okay, these two external nodes will come here, right? Again, when you merge this red node here, when you merge this red node here, okay. So when you merge this red node here, this 20 and 30 will go up. Okay, this 20 and 30 will go up, and this all these external nodes. Previously, this external node is already merged here. All these are merged here. Okay, so these two external nodes will become one external node, and these two will become one external node. Okay, and it will come at this level, right? Okay. Similarly, when you merge this red node here, these two external nodes will become one external node, and it will come here. Okay, so finally if you see, all the external nodes will be at one level. Finally, if you see what happens, all the external nodes will come at one level, right? Yeah, here it is not two nodes is not merging. See here, uh, only this node got merged here. Okay, this, so we can say that this 20 will go up. Okay, this 20 will go up. Okay, right? So this 25 will come here. Okay, right? 25 will come here again. 25 will come here. Okay, again the 25, the child, there is no child for 25, but this will also merge there. Okay, so finally what happens, in the sense, all the external nodes will come in this level, right? So that is what that property says. Okay, so this is how the merging is happening. These two got merged here. Okay, and this got merged here, this got merged here, and this got merged here, right? Fine. Now let us see how we insert a new node into a binary search tree, okay, into a red black tree. So when you insert a new node into a red black tree, there is a question: what should be the color of the new node? Should it be black color, or should it be red color? Okay, it should not be actually black color. The reason is the reason is why it should not be black color, in the sense, say new nodes will be always inserted as a leaf node. Okay, so 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 the previous node, this can be either in red color or in black color, we don't know. And how many child it has previously, does it has any other child also, that also we don't know, right? Okay, if it does not have any child, if it does not have any child, and for the new node if you give a black color, then what will happen? Then number of black nodes in one of the path will be more than the number of black nodes in other path. Okay, say if this is a red color, if previously this node, this is a old node, which is the right child of the particular parent. Okay, if this is a red color, and now you are inserting this new node, okay, which is in the left side, and you are giving this as a black color. Now what will happen, because of this new node, as it is a black color, the height of the tree from root to external nodes in one path, the number of black nodes will be greater than, will become greater than in other paths. Okay, so one of the properties says that the number of black nodes from the root to the external nodes should be same in all the paths. So this will violate that. This will violate that principle. So you cannot have a black node. You cannot give a black color for the new node. Okay. So if you give what will happen? One route to external path has an extra black node. Okay, or an extra black pointer. Either way, right? So we have to so and if that happens, to rectify that problem will be very difficult, right? So it is better to go with a red color for the new node. When you go with red color, what happens? One route to external node path may have two consecutive red nodes. Okay, this may happen, but this may happen. So already this previous node is red in color. Now you are inserting a new node, and for this new node, we are saying that you give red color. Now what happens? This child and parent both have red color. Okay, so this may violate the property 4. This may violate the property 4, but this can be rectified easily. It is not difficult to rectify. Okay, if you keep it as a black node, rectifying it becomes very difficult. Okay, so we go with red color. That doesn't mean that if you give a red color for the new node, it will not create any problem. It may create problem because the parent also may be red color. In that case, two consecutive nodes should not be red. Okay, so we say that the tree is unbalanced or imbalanced. Okay, so but this imbalance can be rectified either by changing the color or by rotation. Okay, this imbalance can be rectified either by changing the color of the node or by rotation. Okay, so that is what we are now going to discuss in detail. Okay, so so what we have understood from this particular slide in the sense, the new node should be in red color. It should not be in black color. If it is in black color, then the number of black nodes in one of the path will be more than the number of black nodes in another paths in other paths. Okay, so the option of giving black color for the new node is ruled out. Okay, so we have to go with red color for the new node. But when you give red color for the new node, if the parent is also in red color, then we say that the tree is imbalanced. In that case, the tree should be balanced. So that can be done either by changing the color of the nodes, by changing the color of some of the nodes, or by performing rotation. Okay. So how to do that? When to change the color of the nodes and when to perform rotation? That's what we are going to discuss in this lecture. So this slide, I'll come to this slide later because this is some top level understanding. First, let me discuss the concepts with an example. Then we will come here. Okay, fine. See, these are the possible imbalances that may get created. Okay, so there is a spelling mistake here. This imbalance. Okay. So these are the possible imbalance that may be created. Okay, in a red black tree. What are the imbalance? The first type of imbalance is called as L. So totally you can see there are 8 type of imbalances. The first type of imbalance is called as LL or imbalance. So what is LL or imbalance in the sense? See, we identify totally 3 nodes. One is the new node which you are inserting. Okay, the new node. Better I will use some other color instead of red color. I'll use green color. Okay. See, one is the new node that we are inserting. The other one is the parent of the new node. Okay. The other one is the parent of the new node. The other one is the grandparent of the new node. Okay. Right. So the new node, say let us call the new node as what is the convention? Yeah. So let us call the new node as U. The new node is called as U. Okay. The new node is called as U. Okay. I'm trying to explain what is meant by LLR. Okay. The new node is called as U. The parent of new node is called as PU. P represents P, parent. P represents parent of U. Okay, and this node is referred as GU, which is grandparent of U. This is grandparent of U. Okay, when so this if this new node if this new node is coming as a if this new node is coming as a left child. Okay, right? If this new node is coming as a left child of the parent, okay, and if the parent is coming as a left child of a grandparent, then we say it is LL imbalance. Okay, this is similar to AVL. Up to this, it is similar to AVL. Okay, if the new node is coming as a left child of the parent, and the parent is the left child of the grandparent, then we say it is LL imbalance. Okay, and what is this OR? This OR actually refers to the parent sibling. This OR actually refers to the parent sibling. So this is parent and this is the sibling of the parent. What is its color? If the parent sibling color is red, if the parent sibling color is red, then we say it is LL or imbalance. Okay? Then we say it is LL or imbalance. See, this is new node. So what should be its color? We discussed new node should be always in red color. Okay? And here we say it is an imbalance. When we say it is an imbalance, only when the parent and the child has the same color, then only we say it is an imbalance. So it means that this is also red color. This is already guaranteed for us. Only if these two are in red color, we say that it is an imbalance. Okay, after inserting a new node will be always red color. Then you have to check what is the color of the parent. If the color of the parent is also red, then we say it is an what imbalance? It is an imbalance that we will identify. Then we have to identify what type of imbalance it is. Okay. If new node is inserted as a left child of the parent and if parent is the left child of grandparent, then it is LL imbalance. Again, if the sibling of the parent is in red color, then we say it is LL or imbalance. Okay. If it is LL or imbalance. Okay. So so you can say, see here, if it is a L, if it is a R kind of imbalance, that is if the sibling is in red color, wherever the sibling is in red color, there it is just enough to perform recoloring. Wherever the sibling is in red color, it is just enough to perform recoloring. You need not rotate. Okay. So what kind of recoloring we should do? We should not change the color of the new node. New node should be always red. Okay. So whose color should we change? The color of the parent should be changed. So make the color of the parent to black because two consecutive red is not allowed. Okay. Make the color of the parent sibling also to black. Okay. Make the color of the parent sibling also to black. Okay. Then what you do? Then what you do? See, this can be either red or black. We are not bothered. Grandparent can be either red or black. Now, okay. But here there is one catch. You have to check whether grandparent is a root node or not. If grandparent is a root node, then it should be black color. Okay, because the one of the rules says that the root of the red black tree should be black in color. Okay, so if this is suppose the root of the tree, then it should be in the black color. Okay, otherwise it can be in any color. Okay, fine. Then there is another case, another important point. Say if the grandparent is not the root, if the grandparent is not the root and if it is in black color, then no issues. If it is in black color, then no issues. But if it is in red color, but if it is in red color, then once again you have to check what about its parent. What about its parent? Is it red color or not? If it is red color, then you have to blah 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 everything. Okay. So now you have to make this grandparent as U and grandparent's parent as PU. Okay, and its parent as GU. Okay, and again you have to do all the process. Are you getting? So that should be repeated again. Again you have to check what type of imbalance is it. Is it LL, LR or RL, RR or RL, and accordingly you have to take the appropriate step. Okay. Here we have discussed only LL imbalance, LL or imbalance, right? I think the thing is clear. So first, so imbalance, when we say imbalance, If the new node will be always red color, and if the new node's parent is also in red color, then we say it is a imbalance. Okay, so then we say it is imbalance, and then you check whether it is whether the new node is the left child of parent and parent is the left child of GU. Then it is LL imbalance. Then check the parent sibling. If parent sibling is in red color, then you can just uh, rebalance by changing the color. Okay, right? So this is about LL or imbalance. Okay, so let me. So here is the diagram. So here you can see this is the new node added. So here the red nodes are shown with white color. Okay. So all these are red. This black are shown in shaded color. Okay. Where there is a shade, it is a black. Where there is no shade, it is red. Okay. So new node is always in red color. Okay. And its parent is also in red color. So it is an imbalance. Now new node is in what side of the parent? Left side. And parent is in what child of the grandparent? Left. Okay. Now you check the color of the parent sibling. So parent sibling is this GUR. GUR means grandparent's right child. Okay, GU is GU actually it is grandparent's right child. Okay, grandparent's right child, and here this R represents, it is red in color. It is red in color. This itself shows it is a right child. Okay, this pointer itself shows it's a right child. This or represent that it is red in color. Okay, so with this info, parent is a left child of grandparent and the new node is a left child of parent. With this we know that it is LL imbalance. Here the right sibling, the sibling of the parent is red in color. So with this we know that it is LL or imbalance. Okay? So if it is LL or imbalance, you just recolor it. Nothing else to do. Okay. So what kind of recoloring we should do? We cannot change the color of the new node. So what you have to do is change the color of the parent. Change the color of the parent. Make this parent color to black. Okay. And also you can change the color of the grandparent. Okay. So grandparent color is previously black, now it is made to red. But here, before making it to red, you have to check one thing, whether grandparent is a root node or not. If it is root node, you cannot make it red, it should be in black color. Okay. Otherwise, you can make it red. If it is not a root node and if you are making it to red, then you have to check. What you have to check? You have to again make this as U, its parent as PU, and that's grandparent as GU, and once again uh, those steps you have to repeat. Okay, so this is the procedure. Okay, this is the procedure for LL or imbalance. Right. Next is L or imbalance. Say now we are adding a new child here. This is in red color. Okay, its parent is also red color. So it is an imbalance for sure. But now this new child is added as a right child of the parent. New node is added as the right child of the parent, and parent is the left child of grandparent. Okay, parent is the left child of grandparent. So what is it? It is L or imbalance. But whether it is L or R or L or B, that will be known by the right sibling or by the sibling of the parent. So parent sibling is in what color? It is in red color. Parent sibling is in red color. So it is L or R imbalance. Okay. So whenever it is an R imbalance, you need not rotate. You can just change the color. So again, which color should be changed? Again, which color should be changed? It means we should change the color of the. We will not change the color of the new node. We will change the color of the parent. PU color is changed. Okay. This sibling color is also changed. You can see here its edge. Previously, its edge is red in color. Now it is changed to black. Here also you can see after previously this is edge is light color, which means this is red. Now it is in black color. Okay, it is in black color. So no more it is a white child. No more it is a red child. Now it is a black child. Okay, right. Okay, fine. Okay, so this, see, this R may represent, I think it is representing the right child, but with this pointer you can know whether it is a red or black. So as it is thin, it is red. Now it is in dark color, so it is black. Similarly, when you change this, we are changing this also. Okay, it may be either a, what do you call it? Maybe either an leaf node, external node, or maybe a node may be there, but irrespective of that, we'll make it black. Okay, right? Then the grandparent also we will change it to red color. But again, the same condition applies. If the grandparent is a root node, then you have to keep it as black color. If it is not a root node, you can keep it as a red color. Then again, you have to make this as U and its parent as PU and its grandparent as GU, and the same thing should be repeated. Okay, until you reach the root. Okay, right. Um, so this is about LLR and LRR imbalance. Right? Okay. So these two cases we have discussed. Next, we will discuss about LLB and LLRB imbalance. Okay. So this is the case for LLB imbalance. Here we are adding a new child. Actually, the new child is not shown here. This is the new child. Let us assume this is the new child U. Okay, this is the new child U. Okay, and this is the parent of U, and this is the grandparent of U. Now this new child is in red color. PU is also in red color, so it is an imbalance. Now where is this new child? It is to the left of the parent, and where is PU? It is to the left of the grandparent. So it is sure that it is a LL imbalance. Now whether it is LLR or LLB, for that you should know what is the, for that you should know what is the color of the parent sibling. So if you see the color of the parent sibling, here the node is not shown, but you see the edge color. Edge is dark, so it is black. So it means this child is actually a black child. Okay, either a node is here, or if it is external node, it is black. Okay, so now it is LLB imbalance. Okay, whenever there is a LLB imbalance, whenever there is a B kind of imbalance, black imbalance, that is if the parent sibling is black, then you have to perform rotation. Okay, as long as the parent sibling is red, we can go with recoloring. If the parent sibling becomes black, then we have to rotate. So this is just a LL imbalance. So it means you have to perform a right rotation. So the rotation principle is similar to that of AVL. So just to perform right rotation on the grandparent. Okay, when you perform right rotation on the grandparent, what will happen? PU will become the root of the tree, parent will become the root of the tree, and grandparent will become the right child of PU. Okay, right? Grandparent will become the right child of PU, and PU's left child, PU's right child, whatever PU's right child, that will become the left child of grandparent GU. Okay, so I think it's clear. PU becomes the parent, so GU goes down. Previously, whatever the right child of PU or the right subtree of PU, that will now become the left subtree of GU. That will become the left subtree of GU. Okay, and the left subtree of PU, here the actually U comes, that will come as the left subtree of PU. Okay, so this is the rotation you have to do, right? But after rotating, you should also change the color. After rotating, you should also change the color. Okay, so what is the color change here we are doing in the sense? What is the color change here? Here we are doing in the sense, uh, the new node is this. This is the new node. Okay, so this should be in red color. So this should be in red color. Okay, so this is in red color. So PU should be made black. Okay, PU will be made to black color, and GU also will be made to red color. Okay, GU also will be made to red color. Okay, so so this is the change, color change we are going to do. Okay, so this is the case for LLB imbalance. If it is L or B imbalance, so now we are adding an what do you call? You are adding a new node. This is U. Okay, so this is in red color. Its parent is also red color, so it is an imbalance. Now, what kind of imbalance it is? U is the right child of PU, and PU is the left child of GU. So it is LR imbalance. Okay, whether it is L or R or L or B. For that, you have to check what is the parent sibling color. Parent sibling is black, so the edge is in black color. So it is L or B imbalance. As it is L or B imbalance, whenever there is a B imbalance, you have to perform rotation. So it is L or, so you have to perform two rotations, one left and one right rotation. Okay. So perform left rotation on GU's left child. On PU, first perform a left rotation. Okay. On 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 GU, on PU, first perform a left rotation. So when you perform a left rotation, what will happen? There is no change in GU. GU is here as it is. When you perform a left rotation, you will become the left child of GU. You will become the left child of GU, and PU will become the left child of U, and PU will become the left child. This is PU, and PU will become the left child of U. PU's left subtree is PUL as usual. PU's left subtree is PUL. Okay. What will happen to U's left tree, left subtree? U's left subtree will become PU's right subtree. U's left subtree will become PU's right subtree. Okay. And and U's right subtree will be UR as it is. Okay. U's right subtree will be UR as it is. Okay. And to the G's right, you have as usual GUR. Okay. You have GUR. Okay. This is so this is black in color. Uh, this is black. So this node is also black. Okay. UR is black. This is black. UL is black. PUL is black. Okay. U is in PU is red color. PU is red color. U is also red color. Okay. GU is currently black color. Okay. GU is currently black color. So this is after performing left rotation. Now you have to again perform the right rotation. When you perform right rotation, when you perform right rotation on B, that is on GU, you will get this. It is GU, U will become the root of the tree, U will become the root of the tree, and GU will become the right child. Okay, this is GU, GU will become the right child, and right of GU is GUR, and what will be the left child of GU? Previously, whatever to the right of U, that is UR, will become the left of GU. Okay, and to the left of GU is as usual PU, PUL, and UL. Okay, so you have to perform a left rotation and a right rotation. Okay, after performing the left and right rotations, you see where is U now. You see where is U now. U has now moved to the root of the tree. U has now moved to the root of the tree. Okay, so PU previously U is in the what you call in the bottom level. That is as the U is the leaf node. Okay, so whenever we add a leaf node, we give it red color. Okay, but now U has moved to the top top. Okay, that is it has become either the root of the tree or it has become root of the subtree, or at least it has become the root of the subtree. So now you just make U as black and use child as red. That's it. Okay, now make U as black and use child as red. Okay, so whenever you perform a rotation, we can make this change as constant, that whatever the root of the subtree as black and all its child will become red. See, it has two child only. It can maximum have two child only, both child will be red. Here also that is the case, and here also that is the case. Okay. So this is how we perform LLB and LLRB imbalance, balancing. Similarly, you can work out for RRR, RLR, RRB, and RLB. Right? And now let us discuss with some example how insertion is in fact is happening. Okay. So here is a binary red black tree. Initially, this is the tree like this. It is a red black tree. Okay. First, we are inserting in node 70. So the insertion logic is similar to that of a binary search tree. So as usual, 70 is greater than 50, so go right. 70 is less than 80, so go left. So 70 is inserted here. After inserting, you check whether what is the so new node will be inserted in red color. What is its parent color? Black. So no, it has not created any imbalance. so no issues. Next we are inserting 60. 60 is greater than 50, go right. 60 is less than 80, go left. 60 is less than 70, go right, go left. So it is inserted here. Now this is the new node. Its color is red. What is its parent color? It is also red. So it has created an imbalance. Now what imbalance it has created? The new node is the is what child of the parent? It's a left child. And parent is what child of the grandparent? Left child. So the kind of imbalance is LL imbalance. Whether it is LL or LLB. Check the parent sibling. This is parent sibling 90. What is its color? It's red. It is in red color, black or in black color, and this nothing, no color means it is red. So it is red color. So it is LL or imbalance. So whenever it is a or kind of imbalance, small or, okay. Whenever it is a or kind of imbalance, it is LL or imbalance. Whenever it is a or kind of imbalance, it is just enough to recolor. Okay. So what should we recolor? We will not recolor the new node, especially when it is the leaf node. So rather we will recolor the nodes parent and the grandparent. So make the parent as what do you call? Make the parent color to black and make the grandparent color to red. Okay. But before making the grandparent color to red, check whether grandparent is the root of the tree. No, grandparent is not the root of the tree. So if grandparent is not the root of the tree, then after making grandparent red, you have to check the grandparents. I mean, then you have to make the grandparent as U and its parent as PU, and you have to check it's both the color. Now this node is red color and its parent is black color. So that won't create any imbalance, right? Then next we are inserting the node 65. 65 is greater than 50, go right, less than 80, go left, less than 70, go left, greater than 60, go right. It comes here. Again 65 is inserted as a red node. New node should be inserted as red node. New node should be inserted as a red node. Check its parent color. It is also red. So it is an imbalance. What type of imbalance it is? New node is what child of the parent node? It's the right child of the parent node. And the parent is coming as what child of the grandparent? It's the left child of the grandparent. So it is what kind of imbalance? L or imbalance. Again, whether it is L or L or B, check the parents, what do you call? Sibling. 60 is the parent. There is actually no sibling. Parent sibling is a null node. So null node we assume as black color. Null node we always assume as black color. So it is what type of imbalance? It is a L or B imbalance. Whenever there is an L or B imbalance, you have to perform rotation. So you have to perform a left rotation at parent and right rotation at grandparent. So first perform left rotation at parent. When you perform left rotation at parent, what will happen? This 70, after 70 you will get 65. Okay, then you will get 60. This is what will happen. Okay, this is what will happen, right? Now you perform a right rotation on 70. When you perform right rotation on 70, 70 will take the place of 80 and 80 will become the right child of 70. Okay, right? So when you perform a right rotation, uh, so it is L or imbalance, right? It is L or, so first perform a left rotation, then perform a right rotation. Okay, see, okay, this part, right? So this part, when you perform a right rotation, when you perform a right rotation, so first when you perform the left rotation, you got this, okay? So when you perform the right rotation, what happens in the sense 65 goes up, okay? Yeah, when you perform the right rotation 65 goes up. Okay, 65 will become the root of the tree, and 70 will become the right child of 65. Okay, 70 will become the right child of 65, and 60 is already the left child of 65. Okay, there is no other child for 60 or 70, so there is no other shifting. Okay, so this is the resultant tree you are getting. Okay, so we discussed that. So this is the root of the subtree. Make that root as black and both its child as red color. So that's it. You need not do any other further checking. So that will ensure that the tree is balanced. Next we are inserting 62. So when we insert 62, it is becoming, again it is becoming a left right imbalance. But now again it is a left right imbalance. Now it is a L or R imbalance, because the parent sibling is in red color. Okay. So now we need not perform any rotation. It is just enough to change the color. Okay. So change this color to black. Make 60's color to black. So 60 has become black. And make 65's color to red. So 65 has become red. Okay. But when you make 65 to red, again you have to make this, check you out whether it is a root node or not. So it's the root of the tree or not. It is not root of the tree. So you can make it as red color. But again you should make this as U, this as PU, and this as GU. Now check GU and PU. What is GU and what is PU? Both are red. So again there is an imbalance. So what type of imbalance it is? Now U is what child? U is the left child of 80, and GU is the right child of, and PU is the right child of GU. So this is RL imbalance. It is RL imbalance, and whether it is RL R or RL B. For that you have to check the parent's sibling. For that you have to check the parent sibling. So parent sibling is black in color. Okay, this is the sibling of parent. Okay, it is black in color. So it is actually RL B imbalance. So whenever it is an oral B imbalance, you have to perform, whenever it is a B imbalance, you have to perform rotation. So now what rotation we have to perform? We have to perform right rotation first on parent. Okay. Then we have to perform a left rotation on on grandparent. Okay. So when you perform right rotation on parent, when you perform right rotation on parent, what will happen? 65 will come here. Okay, and 80 will become the, 65 will come here, and 80 will become the right child of 65. 80 will become the right child of 65, and 90 is as usual the 9 right of 8, right of 8. And when 65 comes here, this 70 will become the left child of 80. Okay, 70 will become the left child of 80. 70 will come here. Okay, and 65's left child will be 60. That is as usual. Okay, and 60's right child will be 62. Okay, okay, 60's right child will be 62. So this part of the tree will be converted something like this, right? Okay, and 50 is the GU. Okay, so this is after right rotation. Now you have to perform a left rotation. When you perform left rotation, 65 will become the root of the tree. 65 will become the root of the tree. 50 will become the left child of 65. Okay, and previously whatever the left child of 65, that will become the right child of 50. Okay, left child of 65 is nothing but 60 and its right child, so that will become the right child of 50. Okay, right. So after making this, 65 becomes the root of the tree and also root of the subtree. So just make this as black color and make its two child as red color. Right? So this is how insertion happens in a red black tree. Okay, fine, let us stop this here. Thank you.